Morning, Aussie. Starting with a test today. What's this? Huh. That's water, of course. Water, H2O. Oh, really? That's water, is it? Water's black. Water smells. Aussie, this is water. Does that even look like that? Oh, well, okay. I guess then it's ink, it's black ink. It is indeed, it's black ink, and the black ink is being used to write a chemical formula. Let's just get this right. There's the stuff. Here it is. There's the name. What's its name? Water. And there's its chemical formula. The distinctions are important. What's this? Sodium chloride, Prof. That's black ink being used to write the formula of sodium chloride. That's that white stuff that we put on our sausages, and that's the formula of that compound called sodium chloride. You're quick, Aussie. Okay, what's this? Prof Bob. That's you, Prof. That's you, Prof Bob. No, Aussie. No. This is me. That's my name. That tells you something, gives you some information about me. But this is me. Now, there's a very famous painting by an artist called Magritte. I've got it up here on the screen. Have a look at that. The caption, "Ceci n'est pas un pipe," in French translates to, "This is not a pipe." Ceci n'est pas un pipe. That is not a pipe. It's a representation of a pipe. It's a picture of a pipe. This is a pipe. The distinction's important. If I talk to you about ethanol, the picture I want you to have, your mental image, is some ethanol. This stuff, not the formula C2H5OH. Now, even so, we do use formulas for communication, and it begs the question of the day, what does a chemical formula mean? Here are the formulas of two compounds. The formulas of two compounds. Formula of carbon dioxide, the formula of sodium chloride. These are information about the composition of these two substances. And the way we interpret this information, to interpret properly, you have to know something about these substances to do that properly. And we'll come to that shortly. Now, if we had a microscope, more powerful than anything that you could possibly imagine, more powerful than anything we could get, what do you think we'd see if we looked into a sample of gaseous carbon dioxide? Well, you told us about that, Prof. There'd be these molecules, trillions and trillions and trillions of them, dashing all over the place, bumping into each other and bumping into the walls. Each molecule of carbon dioxide doing its own thing, and a separate little, what's the word you used? Entity, each one of them. You're right, molecules dashing all over the place, billions and billions upon them, flying all over. Each one an identical CO2 molecule. So what do you think the formula CO2 means? Well, it's like you said, it's information about carbon dioxide, its composition, and I guess it means there's one carbon atom and two oxygen atoms. Oh yeah, so if I had a box like this full of carbon dioxide, in there there'd be one carbon atom and two oxygen atoms? Really? That all? No, of course not. There'd be trillions and trillions and trillions of them. Okay, I guess, the formula is telling us about the composition of each molecule. Each molecule's got one carbon atom and two oxygen atoms. How's that? And there are millions of them, all the same. Yep, that's it, Aussie. The formula represents a summary of what chemists know about the composition of carbon dioxide molecules. Each one has got one carbon atom, two oxygen atoms. How they know that, we'll worry about some other time later on. All right, what about this formula? Well, I guess that tells us that every molecule of water, which is identical to every other molecule of water, has got two hydrogen atoms in it and one oxygen atom, just corresponding to the CO2. Okay, good. And what does this formula tell us? We've got three atoms in these molecules. Think about one of them. There's two hydrogens and one oxygen. What does this formula tell us about what's joined to what? Which atoms are joined, connected to which atoms? Oh, easy. That's okay. An oxygen joined to two hydrogen atoms. And how does this formula tell us that that's the structure of a water molecule? Was it? How'd you get that? We learned that at school years ago. Everyone knows that. Every guy on the street knows that that's what the water molecule looks like, what its structure is. Yeah, but I didn't ask you what we know from other sources. I asked you what this formula tells us about the structure. And it doesn't tell us anything. It only tells us about the relative number of atoms of each type of element in a molecule. Nothing about what's joined to what. You've let your knowledge about structure influence what you thought this was saying. Chemical formulas, this sort of chemical formula, tells us only about composition. Okay? What about the formula? What does that tell us about what's joined to what in a carbon dioxide molecule? Well, I guess nothing, Prof. It tells us that each atom has got a carbon atom and two oxygen atoms. It doesn't tell us anything about what's joined to what the connections are. Good. And what about the formula for glucose? C6H12O6. Same deal. Every molecule of glucose has got 6 carbon atoms, 12 hydrogen atoms, and 6 oxygen atoms. And it doesn't tell me anything, and I've got no idea about which of these 24 atoms are joined to which in a molecule of glucose. Exactly. Sometimes actually we do use formulas in a way that shows a little bit of the structure. So for example, ethanol we often write like this, C2H5OH. If you wanted its compositional formula, it would be C2H6O, and all that tells us is that in every molecule there are 2 carbon atoms, 6 hydrogen atoms and 1 oxygen atom. This actually tells us something about what's joined to what in this part of the molecule. And we do that just to put it into the category of alcohols, all of which have got that little bit of structure in their molecules. But compositional formulas strictly only tell us about what's in there and nothing about the connectivity. Okay? Now, what about the formula NaCl, sodium chloride. Every molecule of sodium chloride has got one sodium atom and one chloride ion. Oh, really? Remember last week we had a test on ionic substances, of which sodium chloride is one? Molecules of sodium chloride, really? Yeah, you're right, Prof. It's a bit embarrassing. I got 95% on that exam, and I remember answering specifically that there are no molecules in sodium chloride. There are sodium ions, positively charged, surrounded by negatively charged 6, I think, chloride ions, and each one of those is surrounded by positive sodium ions, and each one of those by chloride ions. So the whole thing is this electrostatic force holding each other together. Yeah, just a reminder, look at the representation on this screen. This is a portrayal of a tiny, tiny piece of sodium chloride structure, crystal. The sodium ions, represented by the small white ones, each is surrounded by 6 chloride ions, represented by the large orangey browny ones, and each chloride ion is surrounded by 6 sodium ions, and they're all held together by the electrostatic forces of attraction between positive ions and negative ions. Okay, so if I can just draw roughly a little bit of that, just imagine one little tiny chunk. There's a sodium ion, chloride ion, chloride ion, chloride ion, chloride ion, and then and there's a chloride ion on top and behind, and each of these is surrounded by sodium positive ions, and each one, this one, this one, this one, and each of those. This is not joined to this chloride any more than it's joined to that chloride. It's joined to all of them equally, all 6 of them. There's no identifiable unit that constitutes what we might call an entity travelling around separately, a molecule or an ion pair. That's not the case here. Everything is equally attracted to everything else around it. So what on earth does this formula NaCl mean? In fact, all it can tell us is that in a crystal of an ionic compound, it tells us about the relative numbers of positive ions and chloride ions. In this particular case, this formula is not telling us about the composition of the molecules of sodium chloride. They don't exist. It tells us that in a chunk of a crystal of sodium chloride, there's an equal number, 1-to-1 ratio of sodium ions and chloride ions. Okay? And you can't know that unless first of all you know something about the structure of sodium chloride. It's a different interpretation of the formula altogether. So what about the formula, let's say magnesium bromide? Can't fool me this time. That's an ionic compound, metal, non-metal, and the ratio of magnesium positive ions to bromide ions is 1-to-2. There are twice as many bromide ions in the crystal as there are magnesium positive ions. And I guess it doesn't tell me anything about the way those ions are packed into each other, amongst each other. Yeah. And another example, excuse me, Matea monkey, copper sulfate, CuSO4 is a formula for copper sulfate, ionic compound. What does that formula tell us? It's a bit more complex. Ionic compound. There'd be copper positive ions, and there are sulfate ions, SO4 2-. So there's copper, they're 2+ ions, aren't they? And there are sulfate 2- ions. So in that crystal, there are an equal number, 1-to-1 ratio of copper ions and sulfate ions. And of course, that's why the crystal has got 0 overall charge. Yeah, so summarising, there's a difference, a distinction between how we interpret formulas of molecular compounds from the formulas of ionic compounds. In the case of molecular compounds, it's the actual number of atoms of each type of element in the molecule, that entity that moves around separately. And in the case of ionic compounds, it's just a ratio of the number of ions of the different sorts. So in fact, to interpret formulas correctly, we actually need to know a little bit of chemistry first. Aha! I didn't realise that.